Hi. Hello. Today, I'm gonna, as I said yesterday, I'm gonna start on a new topic, which is maximum likelihood estimation. You guys take your seats, please. All right. So now, before I do that, let me thank you, all of you who completed the week 3 feedback form yesterday. I really appreciate you taking your time. I really appreciate you taking your time to complete the week 3 feedback form. And if you haven't done so, it's not too late to do, because if you haven't completed it, you can still complete it today and give it back to me later. Okay? Now, let me just, there are a few points. Hello? There are a few points I like to respond to with respect to the comments some of you wrote. The first thing is, I think most of the comments, most of the comments are very positive. I'm really pleased about that. And if you want to look at all the comments that all of you wrote, you can go to the website, the course website, and you will see or you can read for yourself what all the students wrote about this course. There are a few comments which I need to respond to. The first of them is I'm kind of confused about this, because some of you wrote in your feedback forms that the pace of teaching was too slow, but there were also comments where people said that the pace was too fast, and some people said that the pace was about right. So I'm not quite sure what you actually mean, because I guess it depends on the student. I guess there are there are students of different caliber. So for some students, maybe the pace is too slow. For some students, it's too fast. Some students, it's about right. Anyway, I will take account of this, and I'll try to pick up the space a little bit, if you don't mind. Or is it okay with you guys if I increase the space? Or no? Or is it okay if I keep it like this? Okay, all right. And that's one comment I want to respond to. There was another comment about the, sorry guys, look. There were there were a few students who wrote about the solutions to the example book. Remember, at the first week of classes, I gave you an example booklet, and I think about you will find solutions to many of the questions online. You should go to the course website. You will see that many of the questions in the example booklet are either covered in the problem sheets. You see there are problem sheet 0, 1, 2, up to 6, right? So they're either covered in the problem sheets, or there's another link which says random questions. You see, you should go to the course website. I don't have it with me here, but it says there's a link which called random questions with solutions. That also gives solutions to some of the problems here. And the reason the others, for other questions, there are questions for which there are no solutions. Like, for example, the two questions I did yesterday during the lectures, example 10 and example 11, those, there are no solutions for those, anyway, printed solutions for those. So that's why I actually did them yesterday during the lectures, example 10 and 11, right? And by the end of this course, that is by week 12 or week 11 of this course, I will have answered most of the examples from this booklet. All right? I mean, the reason I haven't given answers to every single example is because it's to help you guys. I think if I give answers to every question, there's nothing for you to do, right? I mean, a good way to build confidence, guys, is to try questions by yourself and see if you can solve a question by yourself, right? But as I said, So by the end of this semester, I will have answered most of the questions either in printed form or in handwritten form, right? I will have answered most of the questions from this booklet. All right, guys? So that's what I wanted to say with respect to this comment. And there was other comments, and there were a few people said that I sent many emails. I mean, you must realize that these emails are not like always automated, right? There are about 300 students taking this course, guys. So sending 300 emails every week, week after week, it's not easy for me. You know, I spend a lot of time doing it, and I hope you guys appreciate that, right? I mean, the reason I send you these emails is just to let you know in advance what I'm going to cover in the upcoming week, so that you can prepare well in advance for the material I'm going to cover in the next week or the coming week. All right. There was also, I don't know whether I should say this, but there was one student. I don't know who this student. I don't want to know who this student is, but. He wrote a very negative comment about my teaching, but I mean, guys, I don't want to make enemies, guys. I mean, I'm just trying to be a good friend of you guys, right? That's why I don't want to make enemies. I don't want to make enemies with any of you guys, because I spend a lot of time teaching this and also sending you support material outside the teaching hours and during the example classes. And I don't think I don't think anybody in the university likes giving you the exam papers for the past 10 years and the solutions, and podcasting all the lectures and the example classes, right? And sending you emails like 300 times every week. I don't think anybody really does that. So I'm only here to help you guys. So I don't want to really make enemies, because I was kind of shocked by this comment, but I don't want. You can read it. You can read the comment yourself because it's online. Okay. All right. All right. Now let's begin, guys. So the first thing I want to talk about today. I'll put it here. The first thing I want to talk about here today is the likelihood. Like I'm sure many of you probably heard this thing before, so I'll be brief, all right? Right? So the likelihood function is basically if you have a random sample x1 to xn with the common PDF fx theta, here theta denotes the parameter, right? Then the likelihood function is defined as the product of the density function over the observations. So in this case, you have n observations, x1 to xn. So it's just the product of fxi, I from 1 to n, right? All right, now you should have a random sample from a discrete distribution. So px, in this case, this notation here represents the probability mass function. Remember, probability mass function is associated with discrete random variables, right? So if you have a discrete data set, then the likelihood is once again, is the product of the PMF at the n observations. So it's the product of pxi, I from 1 to n. Okay? All right, guys. Let's do some, just look at some examples, guys. Right, suppose you have observations, you have IID observations xi coming from a normal distribution with parameters mu and sigma squared, and both parameters assumed to be unknown. So in this case, the likelihood is function of two parameters, mu and sigma squared, and is the product of is the product of the density function. Remember, this is the density function of the normal distribution with parameters mu and sigma squared. Now, if you take the product of this, you will get right? So if you take the product of this, this is what you will get. Now, I must emphasize one thing. I've been teaching this course for the past 10 years, and I found many students, I found many students making mistakes from this line to this line. I really don't understand why, because I found lots of students making mistakes when you go from this line to this line. It's just a matter of algebraic simplification. From this line to this line is simply algebraic simplification. And I do not simply understand why people make mistakes, why they can't simplify this to this correctly. I mean, if you do that in an exam or the test, you'll only get partial credit. I mean, sometimes you will not get any credit if you make a mistake from this to this. Yeah? So it's really important that you learn to simplify algebraic expressions, right? So that's example 1. Now, example 2. Now, do you guys remember this distribution? What is this known as? Huh? Poisson, yeah. So this is a discrete distribution, of course. So here, the only parameter is lambda. So the likelihood of lambda is the product it's the product of remember, this is the probability mass function of the Poisson distribution, right? Now, again, you have to be very careful when you simplify things. So if you simplify this, you will get the following. All right? So this product here simplifies to So once again, I cannot emphasize this enough times. I think it's really important. If you have difficulties simplifying products of functions, please get your algebra correct, because that's one main reason that people lose marks in the exam, as in my experience. Okay. Right, so next thing is all right, the next thing I'm going to talk about today is maximum likelihood estimation. It's on page 15 of the lecture notes, right? I'm going to consider 3 different cases, all right? Case A is where The case A is where the parameter theta is a scalar. You know what a scalar means. Scalar means a singular value, a single value, right? So, for example, like the Poisson distribution, in the Poisson distribution, the parameter, there's only one parameter, so it's a scalar case. And also the exponential distribution, there's only one parameter, so it's a scalar, right? Right, in this case, what you do is the following. You just bear with me, guys. Right. All right. Can you see what I have written, guys? So there are a few steps, but I mean I know it's a long. It looks like it's long, but it's not. So what you do is the first thing you do is to take the log of the likelihood, right, and then you differentiate the log of the likelihood with respect to theta and set it equal to 0. You get this equation, and solve this equation for theta. Call it theta hat. And then you compute the second order derivative of the log likelihood with respect to theta and show that the second order derivative at theta equal to theta hat is a negative number. And finally, if this is the case, then theta hat will be the MLE for theta. All right? So this is the procedure you need to follow in the scalar case. That is, when the parameter of interest is a scalar, there's only one parameter. Okay. Now, case B. Case B is as follows: is where the parameter of interest, uh, is a vector with two components, theta 1 and theta 2. So some examples are like the normal distribution. The normal distribution has two parameters, mu and sigma squared. The beta distribution also has two parameters. The gamma distribution also has two parameters, right? So in this case, all right, so these are the first three steps, and call this equation 1, equation 2. Okay. Right, so the procedure goes like this. So the first step is to write down the likelihood function of theta 1 and theta 2. The second step is to take the log. The third step is to take the partial derivatives of the log likelihood with respect to theta 1 and theta 2 and set them to 0. Call this equation 1, call this 2. The next step is to solve 1 and 2 simultaneously to get the solutions, say, theta 1 hat and theta 2 hat. Now, I missed out a step. The reason I will explain in a minute, because to check, remember here, over here, to check that this is an MLE, we took the second order derivative and made sure that the second order derivative is negative. But in the bivariate case is more complicated because you need to compute something known as a Hessian. You guys done Hessian before? Anybody? You heard about Hessian is a 2 by 2 matrix in this case. I mean, to make sure that this and this is are the MLAs, you need to compute something. It's a 2 by 2 matrix, and you need to prove that that matrix has determinant which is positive, right, in order to show that these are MLAs. But I don't want you to do that because that will take you forever. I mean, if I ask you that in the exam, then you spend the whole 2 hours doing that. I don't want you to do that. So I just missed out that step. So after this step, you just go and say that the solutions that you got here are the MLEs for theta 1 and theta 2, respectively. Okay, guys? Is that clear or so forth? I will do some examples in a minute, but let me consider one more case. This is case C. Yeah? Case C is where the parameter is a vector with k parameters, theta 1 to theta k. There are examples like this. For example, did you guys done linear regression? You have? You probably heard about it anyway. In regression, for example, you have many parameters, not just 2, but sometimes 10, sometimes 20. I mean, you can have any number of parameters in linear regression, right? So it corresponds to such a situation like that, okay? So in this case, you should say MLEs. Derive the MLEs of to derive the MLEs of this, you follow this procedure, right? The first is to write down the likelihood take its log, okay? Solve the all right, solve the following equations. So this is the partial derivative with respect to theta 1, partial derivative with respect to theta 2, all the way up to the partial derivative with respect to theta k. Set them to 0, solve them. The solutions of these equations can be supposed to be the MLEs of theta 1 to theta k. Now, once again, I have skipped one step, because in order to make sure that these are the MLEs, you need to compute the Hessian. The Hessian in this case will be a k by k matrix. So, for example, if k is 10, it will be a 10 by 10 matrix. And you need to show that matrix, the determinant of that matrix is positive. And it's not it's not trivial. I mean, it's not a trivial thing to do. So I have skipped that step, all right? Okay. Okay, good. All right, guys. So now let's do some examples. We'll start with some simple examples. Right. So in this case, you have a random sample from the exponential distribution with parameter lambda, and we want to find the MLE of lambda. So this belongs to the case A. Remember, there are three cases, A, B, and C. A is for scalar, B is when you have two parameters, C when you have k parameters, right? So it belongs to this example belongs to the first scalar case. So the first thing to do is to write down the likelihood function of lambda. Now, what's the density of the exponential? You remember, guys? You remember this is the density function of the exponential distribution, right? Now, if you simplify this, you should get this, right? Once again, make sure that you know how to simplify things, guys, because it's really, really important. It's really important that you simplify the likelihood function correctly, okay? Taking the log, you get taking the log, this is what you get. Yes? Next, you differentiate the log likelihood with respect to the parameter, which is lambda. So it's n over lambda minus and you set this to 0 and solve. So if you solve this equation for lambda, guys, you get what? You get lambda hat equal to n divided by which is 1 divided by the sample mean. Yes? Now, because this is a scalar case, you need to look at the second order derivative of the likelihood, of the log likelihood, right? So the second order derivative is minus n over lambda squared, which is of course negative all the time, right? Yeah, because lambda is positive, right? Therefore, this is so hence all right, hence lambda hat equal to 1 divided by the sample mean is the MLE of lambda. Is that clear, guys, or no? Yes, no? Yeah, I mean, you might have. Okay. Right. Next, let's look at one more example in the this is example 2. Right. This is the, you guys remember the geometric distribution. You know this distribution, right? We did ages ago. It's known as the geometric. You should look in. You should look at page 4 of the lecture notes. You will see we talked about the geometric distribution, right? So the first thing to do is to write down the likelihood function, and the probability mass function is this. Now taking the product of this, you get this. All right, now this equal to I'm sorry to bring this up one more time, but this is one example where students got the simplification wrong. I mean, many times, not just one or two times, but this is one example where they couldn't go from this line to this line. So once again, please, it's for the benefit of you guys. All right, so this is the log of the likelihood, guys. This is the log of the likelihood. Then the next step is to differentiate the log likelihood with respect to p. So you get n by p minus this. All right, so this is the derivative of the log likelihood. Set this to 0 and solve for p. Now, if you solve this for p, you get n times 1 minus p is equal to p times all right, so the np and the np cancel out, so p hat is equal to n divided by the sum of xi, which is once again 1 divided by x bar. Right, now we are not done yet, because this example is once again a scalar case, right? We only have one parameter, so we need to show that the second order derivative, let me put it here, we need to show that the second order derivative is negative, right? Now let's see how we can do that. The second order derivative is the derivative of this guy here, which is now let me ask you, how do you show that this guy here is less than 0? Or how can you be sure? How can you be sure that this thing is less than 0? Yeah, that's right. Yeah, exactly. Remember, xi is greater than or equal to 1 for every I, by definition, right? Because remember, geometric variable is defined from 1 to infinity, 1, 2, 3, up to infinity. So that implies that the sum of xi, I from 1 to n, is greater than or equal to n, right? And this implies that the sum of xi, I from 1 to n, minus n, is greater than or equal to 0. So this guy here is greater than or equal to 0, right? And n is always greater than 0. So hence, this implies that the second order derivative must be negative, right? All right. Hence p hat is 1 over x bar is the MLE of p. All right, guys. I will stop here now. But next time we meet, we will do more examples in case B and case C. I will see you guys tomorrow if you are coming to the example classes. And for any questions on this course, please send me an email or come and see me in person. Okay?
actually, this was after the applicant talk, pump, gauge for pumping something up, metal contraption.
I thought you were going to say breast pump.
No, not the higher.
That's going to be annoying.